jump right in, shall we? You've probably used the concepts we're going to dive into today without even realizing it. I mean, think about it. Every single time you open up Google Maps to check traffic, or whenever you scroll through a social media app and it magically recommends the exact perfect account for you to follow, or honestly, even when your browser just loads a basic web page, all of those daily digital habits run on exactly the same remarkably simple mathematical idea. Welcome to today's explainer, where we are going to break down the incredible world of graph theory. So, ask yourself, what on earth actually connects the logic of routing your car through brutal city traffic to the logic of an app recommending a new influencer to follow? Off the top of your head, it sounds like they should require completely different, totally unrelated technologies, right? But underneath the hood, the invisible link between these platforms is literally identical. They both rely entirely on understanding objects and exactly how those objects connect to one another. Here is our roadmap for today's explainer. Section 1, the invisible math around you. Section 2, what is a graph? Section 3, the vocabulary of connections. Section 4, different types of graphs. And Section 5, why does this matter? Let's get right to Section 1, what is a graph? Stripping away the complexity. Okay, to really grasp this concept, we need to completely set aside traditional algebra. Just toss it out. We're getting rid of x and y coordinates, we're throwing out geometry, shapes, and any notion of actual distance. We are stripping everything down to the absolute bare-bones, raw skeleton of the math. The core definition of a graph is beautifully, almost shockingly simple. It's nothing more than a collection of vertices, which you'll also hear called nodes or points, that are connected by edges, which are simply the lines between them. That's it. That's the whole shebang. You can think of the vertices as cities on a map and the edges as the highways connecting those cities. Bam, you've just built a graph. Or think of a social network. Every single person on there is a vertex, and every friendship is an edge connecting them. When you zoom way out, an entire platform with billions of users is really just one massive, mathematically simple graph. Now, if we want to be formal about it, it looks like this. G equals the ordered pair of V and E. G stands for graph, obviously. V is your set of vertices, and E is your set of edges, with each edge basically just being a pair of those vertices. A graph is entirely defined by these dots and the lines connecting them. It's calm, it's straightforward, and it really is that simple. Moving on to Section 2, the vocabulary of connections, equipping the mathematical toolkit. To make sense of massive networks, we need a few basic tools. Our first tool is degree. The degree of a vertex is simply the number of edges connected directly to it. Let's relate this back to the real world for a second. Imagine you are a vertex in a giant social network graph. Your degree is essentially your total number of friends. If you have exactly 3 friends on this network, you have 3 edges attached to you. Therefore, your degree is 3. Super intuitive, right? Next up in the toolkit, we have the path. A path is a sequence of vertices connected by edges. But here's the absolute key rule. No vertex is visited more than once. Imagine walking from one specific city to another by stepping through a very specific sequence of connecting roads. As long as you never ever pass through the exact same city twice on your journey, congratulations, you are walking a valid path. But you might be wondering, what happens when you actually do want to go back to where you started? Well, that brings us to a cycle. A cycle is a path that starts and ends at the exact same vertex. Think of this as a closed loop. It's like leaving your hometown, embarking on this fantastic road trip through a bunch of other cities, and returning to your own driveway without ever retracing a single road. That specific loop, that's a cycle. And our final core vocabulary word here is the connected graph. In a connected graph, there exists a path between every single pair of vertices. Basically, this means that absolutely nothing is isolated. There are no lonely dots just floating off in the void. Every single vertex is totally reachable from anywhere else in the entire graph, just as long as you follow the right path. These concepts, degree, path, cycle, and connectivity, they form the absolute bedrock of everything else we're about to explore. Which brings us to Section 3, different types of graphs, tweaking the basic graph. Not all graphs are exactly the same. By just slightly tweaking the rules, we get totally different tools. Consider the difference between these two types of connections. On one side, we have undirected graphs. These are mutual connections, where the edges have no direction at all. If vertex A is connected to B, well, B is equally connected back to A. Facebook friendships work exactly like this. The relationship literally has to be mutual. But on the other side, we have directed graphs. sometimes called diagraphs. Here the edges are one-way arrows. They physically point from one vertex to another. Think of Twitter or Instagram for this one. You can follow someone, which draws an arrow from you to them, without them ever following you back. The relationship has a very specific one-way direction. Building on that logic, there are 3 essential graph variations that basically power all of modern technology. First, weighted graphs. In these, the edges actually carry numerical values, things like physical distance, travel time, or maybe even monetary cost. If you ever want to find the fastest possible route somewhere, you absolutely need a weighted graph. Second, we have trees. Now, a tree is a connected, undirected graph with absolutely 0 cycles. None. If you have, say, 10 vertices, a tree graph will have exactly 9 edges. We use trees all the time to organize things hierarchically. Think about your computer's file system or charting out a family lineage. And third, directed acyclic graphs, or DAGs. These are directed graphs with one extremely strict rule: no cycles allowed, 0 loops. DAGs are fundamentally crucial in computer science. They power stuff like complex machine learning frameworks and software build systems, where tasks have to happen in a very specific, unrepeating order. Let's wrap things up with Section 4. Why does this matter? The macro applications. This is where the abstract math translates into the massive, real-world systems governing our modern lives. It's honestly incredible. Take the navigation industry. Every single GPS app models the road network as a massive, weighted, directed graph. It then uses algorithms, like the famous Dijkstra's algorithm, to compute the absolute shortest path to your destination in literal milliseconds. Moving down to the internet, every single web page out there is a vertex, and every hyperlink is a directed edge. Google's legendary PageRank algorithm works by analyzing this unimaginably vast graph to identify which pages are actually the most important. In biology, scientists literally model complex protein interactions within a living cell as graphs. Why? Because it helps them identify critical biological roles and drastically accelerate life-saving drug discovery. And for software compilers, whenever your code is compiled, the system builds a directed acyclic graph, a DAG, just to determine the exact processing order. If there's a cycle in there, the compiler physically cannot proceed and throws a circular dependency error. Graph theory is literally sitting at the structural core of every single one of these massive industries. It is incredibly powerful stuff, but let's bring this explainer all the way back down to its absolute simplest origins: vertices, edges, relationships. What makes graph theory so overwhelmingly dominant in mathematics and computer science isn't that it's highly complex. Not at all. It's its incredible generality. Whenever you have a system of entities that interact in some way, whether it's human beings, web pages, intersecting city roads, or microscopic proteins, you have a graph. And the very second you recognize that you're dealing with a graph, you suddenly unlock decades of brilliant mathematical tools built specifically to solve your exact problem. So, I really want to leave you with a provocative question to ponder today. What kind of graph are you currently standing in? Think about your morning commute. Are you traversing a weighted, directed graph? Look at your own friend group. Is it a fully connected, undirected graph? Start looking at the world around you through the lens of vertices and edges. It kind of changes how you see everything. In future explainers, we're going to dive way deeper into the amazing tools used to traverse these networks, like breadth-first search and minimum spanning trees. But for now, just remember the incredible invisible math connecting your world. Keep learning, keep mapping out your connections, and we will see you in the next explainer.